Greetings and welcome to the AP Physics C video series. This is video 4A, the location of the center of mass. Center of mass is defined as the point that moves as though all the mass of the system were concentrated there. Initially, what we're going to do here is look at locating the center of mass for systems of particles that are static and unmoving. Then for solid objects that are static and unmoving. And then for systems in which the objects themselves are moving relative to each other. So a particle is an object for which we ignore the physical dimensions. We have some experience with this when we model objects as a dot with force vectors acting on it. We treat the particle as if all of its mass is concentrated at one point. Real objects, of course, have physical dimensions, but usually we can say that their locations or their displacements are much larger than their physical dimensions, so their dimensions don't really matter. In a system of particles, we're going to have at least two and usually more particles that are at different locations, and we'll need to locate the center of mass. We can have one or two or three dimensional arrangements. So we'll start simply. We'll start with a one-dimensional particle arrangement. Here we see particles located on a straight line axis. We can identify this as the x-axis, and we can see where the origin is. M1 is located at some position x1, M2 is located at x2, and we want to treat this system as if all of the mass were concentrated at one point. The way we do this formulaically, this is in a red box. As you know, that means it's on the formula sheet. We have x sub cm, so that's the location of the center of mass, equals sigma m sub I, x sub I, over sigma m sub I. The sub I indicates the ith particle. So I goes from 1 to however many particles are in the system. In this case, we only have two. M sub I is the mass of the ith particle. X sub I is the position of the ith particle. So when we look at this particular system here, in the numerator we have M1 X1 plus M2 X2. That's the summation of the mx terms, and then divided by the total mass, M1 plus M2. Pretty straightforward. It's pretty clear that whichever particle has the larger mass will have a bigger influence on the location of the center of mass. If M2 and M1 are equal, then the center of mass would be located in the middle of them, the middle of their two locations. If M2 is larger, the center of mass would sort of shift to the right, in this case towards M2. If M1 were larger, the center of mass would shift to the left. Now, if we have a two-dimensional space or an XY plane, we are familiar with separating the analysis of X and Y directions. Think of analyzing projectile motion or sigma fx and sigma fy. We're going to do this again for the location of the center of mass. We can see that M1 is located at, if we were to list its location as a coordinate pair, x1, y1. M2 is at x2, y2. M3 is at x3, y3. So the formulas look, the x formula is the same as it was before. There is a similar version in the y direction. We sum the mx terms and divide by the total mass. Sum the my terms, divide them by the total mass. And that will give us the x and y coordinates of the center of mass of this two-dimensional system. Since we have three objects here, I have m1x1 plus m2x2 plus m3x3, and then divided by the total mass, m1y1 plus m2y2 plus m3y3. Again, divided by the total mass. Now, I won't try to draw a three-dimensional arrangement of particles, but you can get the idea, realizing that each particle in the system would have an x, a y, and a z component. They would be typically indicated with IJK notation that we are familiar with. This location of the center of mass has a three-dimensional position vector given by the following. The formulas look exactly the same. We now have a third dimension, the z sub cm. We can generalize this considering that R is a generic three-dimensional position vector with xi plus yj plus zk for each particle in the system. So R sub cm, the location of the center of mass in three dimensions, sigma mi ri over the total mass. Okay, so that's fairly self-explanatory. We'll have some examples of this in our daily. And then next we'll move on to solid objects, which are basically collections of particles. And from there, motion of the center of mass. Till next time, we'll see you again soon.